solution, then you have to modify, there's a little wrinkle in this procedure, but we'll get back to that, okay? The first set of problems we're going to do doesn't have that wrinkle. And number 4, what do? You assume a particular solution as a linear combination of all members of the resultant families with undetermined coefficients. That's why it's called the method of undetermined coefficients. But unlike this, or the business we had before, we had arbitrary constants. These constants of combination are not arbitrary. How do you get them? You basically write the particular solution as a linear combination of the family members, and then you demand that it satisfy the non-homogeneous equation, and you'll see you'll get exactly the right number of equations to determine numerically what those coefficients are. Okay? So they're not arbitrary. They're going to be determined by plugging it into the equation. Okay. As usual, this becomes much clearer if we just do some problems. So let's do that. Here's the first example I'm going to do. Okay. Like I said, always make it a habit when you're solving a non-homogeneous equation to first find the homogeneous solution. Okay, so you may say, what does this make? I'll find the particular, then the homogeneous. No, because what happens is that if, as we said, number 4, which we skipped, or was it number 3? Condition 3 that we skipped. If it comes out that a member of the family is a homogeneous solution, you have to make a little change in it, and you're not going to know that unless you have the homogeneous solution first. So always get the homogeneous solution first. So here's example number 1. Okay, we're going to have the second derivative of y with respect to x plus 4 dy dx minus 2y, y double prime plus 4y prime minus 2y equals a quadratic. 2x squared minus 3x plus 6. Okay, so I've got y double prime plus 4y prime minus 2y equals 2x squared minus 3x plus 6. The first thing that we have to do is get the homogeneous solution. Step 1, homogeneous solution. That's really bad English. It's not the homogeneous solution, it's the solution of the homogeneous equation. So what does that mean? The right-hand side is 0 now, okay? Now I got y double prime plus 4y prime minus 2y equals 0. I know how to do that, right? I basically write the characteristic equation, r squared plus 4r minus 2 is equal to 0, right? We're going to have to use a quadratic formula on this guy, right? R equals negative 4 plus or minus the square root 16 minus plus 8 all over 2, which is, of course, negative 4 plus or minus the square root. 16 and 8 is 24, which is 4 times 6, right? All over 2. So the roots come out to be negative 2 plus or minus square root of 6. Right? And those roots are distinct, right? Great. And it's not a repeated root. So therefore, we just have exponential of the first Rx, exponential of the second Rx. So y, now different people have different notation. You could write y sub h or y sub c. I'll follow the book, write y sub c of x. They call that the complementary. Very important when you do this, because a lot of people get screwed up on exams when they do this, okay? We're going to let y of x, that symbol, y, be the solution of the non-homogeneous equation. I can't write y here. Y is not a solution to the non-homogeneous. It's the solution of the associated homogeneous. So make a distinction. Call it y sub c or y sub h. Okay? So you'll know that it's not the complete solution. So the complementary solution looks like some constant, right? E to the power of negative 2 plus radical 6x, right? Plus another arbitrary constant, c sub 2, exponential of minus 2 minus radical 6 times x. That's the solution of the associated homogeneous equation, where C1 and C2 are arbitrary constants. Okay, now let's tackle the particular solution. So I'll use the same symbols that I use over here, ax squared plus bx plus c. Okay? Okay, this one we can do in our head, okay? The right-hand side is a quadratic, right? So what's the family of a quadratic? It's a quadratic. You take a quadratic, you differentiate, you get a linear function. You differentiate linear function, you get a constant. So the family of 2x squared minus 3x plus 6, maybe since we're just starting off, let me just put this over here. What's the family of x squared minus 3x plus 6? Okay, you don't have to break up the factors because it's so simple, right? You're going to get an x squared and x and 1, right? You can do each one individually, right? But then don't repeat it, right? The family of x squared would be x squared, x and 1. And then when you do the family of 3x, it's already included, okay? So remember, the members of the family have to be independent, linearly independent, okay? So you got a quadratic. Clearly, a quadratic and all its derivatives are a linear combination of x squared, x and 1, okay? See the notation, I'll keep the notation the same. Okay, so the particular solution, y sub p of x, is going to be, what's the sheet say to do? It says basically go to the family of the right-hand side and write the particular solution as a linear combination of these guys with undetermined coefficients. So the particular solution will be the form ax squared plus bx plus c. Okay? We've got to get the values of a, b, and c, right? Well, clearly by definition, what's the particular solution? It's a solution of the non-homogeneous equation. So let's plug in yp into here, equate it to the right-hand side, and then we'll match powers. And you'll see you'll get exactly 3 equations of 3 unknowns, and we'll get numerical values for big A, big B, and big C. Well, as preparation for that, we need derivatives, right? So what's yp prime of x? If I differentiate, this guy gives me a 2ax plus b. Okay? Okay, now here when you do, once you set yp of x over here, you have to do the derivative, keep all the constants there. You just can't drop things like we did with the family, right? So 2ax plus b, and clearly yp double prime of x, by differential, I just get 2a. Okay. Now I'm going to do, this is why this notation is so good, what do I mean by L operating on yp? What I'm going to do now is take yp and all its derivatives and just plug into the left-hand side. Okay. First I need a yp double prime. Well, that we found is 2a. That's the first term. And then I need plus 4. Be careful to put parentheses around there because yp prime we found to be 2ax plus b. Minus 2yp. And what was yp? ax squared plus bx plus c. Okay. The algebra obviously gets a little bit involved, even for this simple problem. Okay, what you want to do now is you can equate to the right-hand side, so clearly you want to get, let's rearrange this L and yp instead of this whole mess over here. Let's do the constant, the x term, and the x squared, because I'm equating coefficients. Okay. L operating on yp. Okay, let's get the x squared guys first. There's no quadratic here. Right here we pick up a 2ax squared. Okay, and what about linear terms? Okay, I get over here an 8ax, so that gives me an 8a.
Professor, is that negative 2ax squared?
Negative 2ax.
Where?
On your second L operating on
Your
y
first
line.
term?
Oh.
The first one has a negative.
No, you're good. Over here.
Your bottom line.
Okay, bottom line. Okay.
Yeah.
And you were getting the ax squared.
Yeah, yes, that's right, thank you. Minus 2ax squared. Paying attention there. Okay, so it's a minus 2ax squared, right? And then the linear stuff, we got an 8ax over here, and we get a minus 2bx over here. Right? That looks like. And now we have the constants, right? We get a bunch of those. We get a 2a from back here. Then we get a 4b. And then here we get a minus 2c. Okay. But we know that L operating yp has to be exactly 2x squared minus 3x plus 6. Okay? And these things, the powers of x, 1x and x squared are linearly independent. So the only way the thing on the left can equal the thing on the right for all values of x is if the coefficients of like powers match. Okay. Now when you do this, obviously you want to start with the easiest thing first, right? So when I equate the x squared coefficient, see, look at these guys over here. I only have one thing over here. So that tells me right away, look for the x squared coefficient first. Ooh, 2x squared minus 2ax squared, clearly the value of a has to equal -1, right? That's the only way the x squareds match. And what about the linear stuff? Okay, I have to get a -3, okay? So I've got 8a minus 2b. I'll just do this over here, okay? So I've got 8a, but I know what a is, so it's -8, right? What I'm doing now is I'm going to match the x coefficient, so 8a minus 2b has to equal -3. Well, 8a gives me a -8, -2b is equal to x coefficient, which is equal to -3. Okay, so that says that -2b is 5, right? B is -5/2. Okay, so I got the AB, I'll need one more. And then obviously now I go to the constant, and I said 2a plus 4b minus 2c equal to 6. Let me just make sure I didn't make a mistake on the algebra. Yep, B is -5/2, good. Okay, so yeah, I'm going to just do the arithmetic on the side. 2a is a -2. The 4b is -10, right? Check my arithmetic. 4b, right? -10. And then minus 2c, and that has to equal the constant 6. Okay, so I get -12 minus 2c is equal to 6. So minus 2c is equal to 6 minus 12, which is -6. C is equal to 3.
No,
Did I make a mistake?
I think that's 18, and I think it's
Okay,
-9.
okay, where do I go? Where did I make a mistake?
-12 minus 2c equals 6. You add 12 on both sides. You're supposed to add 12.
Oh, yes, yes. Sorry. So I get -2c, so this is 18, right? So C is equal to -9. Okay. So the particular solution, y sub p of x, is equal to ax squared, which is minus x squared, right? Capital B times x, which is -5/2x. And then the constant cap C, which is 3.
-9.
-9. Check that. X squared minus 5x minus 9. Okay. Now, what's important is that typically you'll be given this equation and it'll say find the solution to this differential equation. Okay? We have two parts of it now. We got the homogeneous solution, right? And the particular solution. And we recall that the general solution to an inhomogeneous equation is just the sum of the homogeneous solution and the particular. Okay? So you lose credit if you stop over here, right? So the complete solution, y of x, is equal to, no, I don't care. You could just say y sub c of x, because we've computed that, plus y sub p of x. Okay? Or you can plug in, if you want to just rewrite it again, you can do that also. So the solution basically is this guy here and that quadratic over there. Okay? And if you did that, that would be fine. Okay? Now it comes out though that suppose that this was an initial value problem where it said solve this differential equation subject to initial conditions. Then unfortunately you got to put the whole mess in for yc and yp because now you have to evaluate the thing at 0 and its derivative at 0 and get simultaneous equations. And that'll give you the C1 and the C2. Okay? And this makes perfect sense now. At this stage, all we have is a second order differential equation, and we know we should have two arbitrary constants. Okay? Yp of x has no arbitrary constants in it. It's determined. There it is, right? But the yc of x, the complementary, which is a solution of the homogeneous equation, has these two arbitrary constants. Okay? The only way you can evaluate them is you need more data, you need initial data. Yeah.
So to get those constants, you'd have to solve it in the complete solution?
Yeah,
or
the complete solution. That's another good. I'm glad you pointed that out. A lot of people make the mistake. Okay, but we're going to do a problem like that shortly. Okay, what happens now is that imagine you were given the initial value problem. It would say find. That's why I told you to be so careful about the notation. Suppose I said find a function of y of x that satisfies this, and maybe y of 0 is 0, y prime of 0 is 5, something like that. Okay? Well, the initial conditions apply to what? They're on y, which is a solution of the inhomogeneous equation. What I've seen students do is they'll apply the initial conditions to yc. Okay? You can't apply it to yp because yp is determined. And that's wrong. Okay? Because it's not yc that has to satisfy initial conditions, it's y, which is the sum of yc and yp. And we'll do a problem like that. Okay? You'll have to, the algebra becomes a little more involved, right? Now you have to just write this whole thing out, plug in the initial values, and solve for C1, C2. But again, very important, if it's an initial value problem, you apply it to the sum of yc and yp, not to yc by itself. And that's why, you see, if you have the notation, you'll know that. What a lot of people do is they'll come over here and they'll just write y of x. And then they'll say, oh, you told me y of 0 was 5. And then they'll use this y. But that's not the solution of the equation. So therefore, put a notation here, y sub c or y sub h, to remind yourself that's not the complete solution.
Would taking the derivative of your complete solution and plugging it back into the initial equation
Give an identity.
It would give you the
Yeah.
same.
Yeah, it'll give you that. And you can think about it, because what's going to happen? Suppose I take y equals yc plus yp. I have this big mess, I plug it in. It's a linear equation, right? I know that the L1 yc is going to go to 0, and the L1 yp, by construction, is going to be the right-hand side. But it's a good check, okay? But again, you don't have to do the whole messy algebra at once. If you wanted to check it, the way I would suggest is basically don't write out the big Y as yc plus yp. Take your yc of x, right over here at this stage, plug it back into the equation, and make sure that it solves the homogeneous equation. Even that can be simplified. Show that this guy and this guy individually do it, clearly the linear combination does, okay? And then for yp, of course, you just take the quadratic that we have over there, okay? Do all this stuff, and I guarantee you'll get 2x squared minus 3x plus 6, okay? That's a nice thing I said, so it's good that you can check these things. Okay. Let's do example number 2. Now, like I said, the algebra involves this kind of message. So I'm going to not do all this, bore you with a lot of the algebra. Okay. I'm going to show you the kind of the essential steps. That's what's important. Here's example number 2. These are all from the book. Some of them I've added, but most of them are from the